So we're going to have a little light entertainment now. Basically, multiphoton ionization with microwaves. So there are atoms, and then we're using dime store photons. That is to say, photons at frequencies of 10 gigahertz. So put that in electron volts or something like 10 to the minus 4. So, in fact, the work that I will discuss actually has been done over some period of time, and there are contributions from people that many of you know, starting with Pierre Pied, then Van Linden, then Van Leupel, Bob Stoneman, who was in Greenfield, Uncontained, Bob Jones, who's there, and more recently Joshua Luria, Richard Overstreet, and Alexander Rack. So what I'm going to do is to say a few words of introduction, sort of set the scale for this, and then I'm going to describe microwave ionization experiments. There are actually a whole lot of experiments I could talk about, but I'm going to try to follow through the notion of microwave ionization and show the similarities that occur in strong field laser experiments. And there are actually quite a few of them. Okay, so first of all, let me introduce my friend, the Rydberg atoms. We're not microwaving ionizing ground state atoms, but we're using Rydberg atoms. So they're atoms in states of high principal quantum number. So the electron is in the enormously large orbit in the Coulomb potential. So if you're in n equal 30, the typical orbital radius is 900 atomic units. So they're really big, and they're really weakly bound, they have exaggerated properties. And so probably the best example of that is how we often detect them. So we don't detect them by looking for fluorescence. We often apply an electric field to them and just push down the Coulomb potential on one side. In fact, that's the potential. And if you actually compute the field that it takes, assume there's no star, the field is given by 1/16^4 in atomic units. So for n equal 20 in laboratory units, it's 2 kilovolts per centimeter. So this is a field that's actually easy to produce. Now, the other interesting aspect of Rydberg atoms is that they're kind of close, since they're not bound by very much, and they're kind of close together. And so I'd like to consider the first microwave ionization experiments that we've done, which were microwave ionization at 10 gigahertz and below. So if I, in fact, look at a bunch of n states, lower down they're further apart, the spacing goes to 1/n³, and higher up they're, of course, closer together. So at n equal 85, it's 10 gigahertz from 85 to 86. It's 20 gigahertz at n equals 70 to 71, and if I go down lower in n, they become even more photons separating the levels. And if you get up to around n equals 600, you can photoionize the atoms with 1 10 gigahertz photon. So the attraction of, well, there are several attractions in using microwaves. One is the conceptual attraction, which is that unlike a focused laser experiment, it's easily possible for all the atoms to see the same microwave pulse. So you do not have this horrendous average over the focal volume of the experiment. It's typically of a focal volume in a laser experiment that is small compared to the atomic sample. In these experiments, it's the other way around. Okay. Of course, the other attractions we have microwave stuff. So the first experiments like this were not done by us, but were done by Jim Bayfield and Peter Koch in 1974. And so they passed a fast beam. So the basic idea of this experiment is to make n equals 65 hydrogen atoms. It was a band of states. And they passed it through a microwave cavity, and they looked for ionization as a function of the microwave field strength at several frequencies. And what they observed is shown here. I mean, this is the graph from their paper. They were comparing it to the Keldysh parameter. But what I find most interesting is if you convert the units from what they use to just field, sort of some experimental plumber like me would do, you find that at n equals 65, if I use a 30 megahertz field, it's 1/9^4. I will show you in a second that this is the same, it's almost the same as 1/16^4. At 1.5 gigahertz, it's still the same field. It's just the static field that's required to ionize hydrogen. But at 9.9 gigahertz, the field is a little lower. At 9.9 gigahertz, which is 10, you're kind of close at n equals 65 to the 2-photon resonance from 65 to 66. And so the field starts going down. But in these cases, the field is really slow compared to the electron motion, and it's just static field ionization. That's all there is to it. Okay, I'll revisit that again later. Okay, so we actually started to do this almost, not quite by accident, but we got into the business of using strong microwave fields actually to study radiatively assisted collisions. But we thought, well, while we're here, let's ionize the atoms too. We don't need to have two, let's see what happens to just one. And so we, in fact, started with lower n states, say states of about n equal 20. And instead, so at n equal 20, the spacing between 20 and 21 is 800 gigahertz. And we were, in fact, using 15 gigahertz microwaves. So there are lots of photons between here and here. So if you think of the hydrogen experiment, you would think that it would be like a static field. So the way that we actually do these experiments, if we did them, I should say, is shown here. So with a laser, we make excited Rydberg atoms, and then we microwave ionize them. And to be a little more explicit, the atoms pass through a microwave cavity, which was just a piece of X-band waveguide that had a septum in it that lets you put a field on it. We evicted the spiders that were in the waveguide. And then if you just close off the ends of the waveguide, you can make a standing wave cavity. So then the laser beams came into the other side of the cavity. It's shown cut in half here. And so then we make a pencil-shaped volume of atoms inside here, but then we only take the ones that are pushed up through the hole in the center to hit our detector. Okay. So the laser excites the atom here. We have a microwave pulse, and then we apply a field ionization pulse that ionizes any atoms that are still hanging around as bound atoms, or it pushes the ions out that are produced by microwave ionization. And although this is somewhat counterintuitive, you get the field ionization signal first, and then the microwave ionization. Okay, the reason that that's true is that if you field ionize them, they don't move until the field reaches the ionization field. On the other hand, if they're microwave ions, they start moving here, and they're out of the cavity, and they never really experience the big field. So what you see is just shown here. It's not out of focus. It's just, if you take things out of phys rev, and they're more than, I don't know how many years old, so with no field, it's this is the 23S signal, and at 230 volts per centimeter, nothing's happened. At 290 volts per centimeter, you can see the ions showing up later. At 408, everything's ionized. So it's either in the initial state or it's gone. Okay? It's really simple. So if you actually do this for, so we would call the point at which you have half of them ionized. So if you plot either, so here we have the bound state signal drops down, the ion signal goes up, and we call this middle point the threshold, mostly because it's the easiest one to measure. Okay. So if you just plot these fields for a bunch of end states, you get the following result. So this has a lot on it. So we can in fact make S or D states. So if you make D states, you can make NM, the azimuthal quantum number of 0, 1, and 2. If you make M equal 2, you only have, you don't have any P and S state, and it looks like hydrogen. And in fact, how it goes so far forward. Anyway, right, so if you make M equal 2, this is the same result they got in hydrogen. I'm not going to talk about it yet. If you excite the S or the D states and you make M equal 0 or 1, you get these points here, okay, which clearly have nothing to do with these. And so at first we thought this is wrong, okay, but it's not. And I'll come back to that in a second. So the M equal 2 states look like hydrogen, and this is why 1 over 9 to the 4th looks like static field ionization. So in the hydrogen atom, atoms in the red-shifted Stark state actually are more easily ionized in the blue state, because the electron's sitting there at the saddle. So the microwave field scrambles up, actually due to the second-order Stark effect, mixes states of the same N, and they just leak out at this point where, where this red state crosses the classical ionization limit. If, in fact, this 1 over 16, 1 over 9 into the 4th is using this N. It turns out if you use the used N that corresponds to this binding energy, it's 1 over 16 into the 4th. And we'll work that out for you right now, but it's very easy to show that. So this is simply over the barrier ionization. That's all there is to it. In the sodium atom, or sorry, any other atom, actually, the levels don't cross like they do in hydrogen. So here, I've just blown up the previous graph. And the space in between the levels is 1 over n cubed. And the star shift at any one of these extreme levels is 3n squared e over 2. Okay, this would be basically the same, but in the other direction. And so the point at which the bluest n equal 8 star state meets the reddest n equal 9 is always this 1 over 3n to the 5th, which is called the Inglis-Teller field, or in plasma physics it used to be called the Inglis-Teller limit, because at that point the star broadening of different levels blurred them together. So this is the field in which we actually observe ionization, approximately. So how we first explain this is the following. That the atoms, say, here at n equal 15, go back, just oscillate back and forth on the Stark levels, and they in fact sample this avoided crossing, which does not exist in hydrogen, with the n equal 16 levels, and so it goes, you could go through this crossing partially adiabatically, and some of them go up in this direction. So if I look then at more levels, I can see here, of course, if I start at n equal 20, I can make this avoided crossing to 21, but I can't go down to 19. And so the only way out of here is just sort of climbing up this ladder and eventually ionizing. Okay. Now, so what I would like to convince you is that this form of microwave ionization, which I've described as simply an oscillating field, is really happening by multiphoton transitions that are shifted into resonance by the AC star shift. So actually we've done a whole set of experiments in potassium that I'm not going to discuss, but I will point out that the first hint of this comes from this. Okay. So this line, so this is actually multiplying the field by n to the 5th. So this line is the field of 1 over 3n to the 5th. That's the actual field of these avoided crossings. But the field that we actually observe ionization is lower than that. And so if you think about if you actually think about the avoided crossing more carefully, it's clear that the levels aren't getting to the avoided crossing, so how are we in fact making this Landau-Ziegler transition so efficiently? Okay. So the answer to that is actually seen by realizing that you're making resonant transitions. So I'd like to quickly go through this. So let's imagine that we start out here in level 2, say, which is shifting up in energy, so in the field, and level 1 comes down in energy. So now, so I'm going to now have a field. So this is 0 field here, and here's my microwave pulse. On each field cycle, what the field does is take the atom from this point up into here somewhere. So in fact, if this is perfectly linear, the wave function never changes. Nothing happens. Okay, that's what happens in hydrogen. But in fact, because of this level crossing, when the field comes out into this region, you admix some of this state into here. So you get a little, you pick up a little bit of amplitude when the field comes out to the extremum here of this state. So now, on the second cycle, it comes back again, and actually, you again can pick up amplitude. Now, if in fact it turns out that this is n microwave photons between them, those two amplitudes add in phase. And in fact, you can treat this problem of adding the amplitudes of successive field cycles exactly like a diffraction problem. And if you ignore the fact that eventually population starts coming back, in low order, the two-level transition probability looks exactly like diffraction. So you could describe this as a phasor sum. So while for all the world the data I showed you looks like it's a field, only a field effect, they are actually multiphoton transitions. Okay, and to some extent you can see this you can see in fact if you excite the atoms in the presence of this 15.5 gigahertz field, you can in fact see in 0 field you just see here's a D state, an S, and then the next D. But then when you add microwave fields of these different amplitudes, when the microwave field gets out to the point where it is where the level crossing is, you can see this 15 gigahertz modulation of all these states. And so they've all basically come into resonance with each other. Okay. Now, as I said, there are many similarities between, something got lost here. Okay, well, I seem to, okay, I threw out one slide. So this is exactly the same thing as what Freeman and Buxbaum observed in a way. I mean, the whole idea of how you get multiphoton ionization, as they pointed out, is when you turn on a laser pulse, in fact, the things shift into resonance, and that's in fact how you transfer population. Okay. All right. So more recently, we've done these experiments in a different way. So we've used something that, if you use a laser, looks much more familiar. Namely, we use a Fabry-Perot cavity, in which we have a standing microwave field. The atoms pass through it, and we excite them in the center of the cavity again. And there are less stray fields, but the other thing that's important is we now detect the electrons. So instead of detecting ions, we detect electrons. And so if I ionize the atoms with the microwaves here, the electrons disappear and we don't see anything when we apply the field pulse. And so in the field pulse, if the atoms are in states of high end, they show up early, and for the low end, they show up later. Electrons basically have zero transit time on the time scale of our problems. Okay. So if I in fact excite lithium atoms to the 46 peak state, expose them to a 38 gigahertz field, in fact, if I look at the atoms that are, all the Rydberg atoms that are left, it goes down as I raise the field amplitude, but it doesn't quite disappear. And actually, if you look more carefully, you find that at states of really high-lying states, they're shown by these red triangles. This is also shown over here. These are grayscale versions of the oscilloscope, trace. So initially, basically, atoms are hard to ionize, and then starting about here, they move up slightly in end, and then we have all the stuff left in very high-lying states. Right. This is not peculiar to using 38 gigahertz. If we use the same frequency we used before, we see exactly the same thing. So, I mean, the bottom line is simply that, contrary to what I claimed earlier, actually, the microwaves don't ionize everything. You wind up with lots of stuff sitting there in very high-lying states. Now, in part, that's because in the earlier experiments we detected ions, but we also had stray fields. Now, this, of course, is, again, something that's not peculiar to doing microwave ionization. Exactly the same, well, I think something very similar, maybe exactly the same thing, was observed by Bob, Doug Schumacher, and Phil Buxbaum 20 years ago, when they found that after exposing krypton and xenon to intense 100 femtosecond pulses, they wound up with about 1% of the population winding up as excited atoms at Rydberg states as opposed to ions. And it's not even confined to just singly ionized species. In an experiment done about 10 years ago, Bob, Eric Wells, and Nitzik observed these Rydberg states converging to the different states, different ionic states of krypton plus. And of course, more recently, at the Max Born Institute, Eichmann and his collaborators observed that when you expose helium to 800 nanometer gigavolt per centimeter fields, that's enough to ionize the ground state. They observed roughly 1% helium plus, sorry, 1% helium excited atoms that had trickled down through all the excited states to the helium, and they concluded that they actually initially formed something like 10% atoms to ions. So exactly the same thing shows up in both of these conflicts. Okay, so, all right, so then I guess what we would like to do is now go on to say, well, what are these states that are surviving? And what can I learn about them? Well, one way that you could learn something about them is to actually take the spectrum in the presence of the microwave field. What I'm interested in is what's this state which lives through the microwave field. So we simply move the laser pulse to the middle of the microwave field, and once again detect bound atoms, which all turn out to be within about 2 microwave photons of the limit. So what you observe is seen here. if you have no microwaves at all, you get the red trace, which is the Rydberg states. And then at the limit, of course, there's nothing detected. So we're detecting the bound atoms, okay? So there are no bound atoms here. The free electrons created at this photon energy disappear during this time. But if I add a microwave field of 16, 28, 45 volts per centimeter, you can in fact see the structure showing up, which has a modulation at the microwave frequency. And you can see two things here. One is the structure seems to be connected to the limit, but perhaps more surprising, this structure goes over the limit, right? I mean, in other words, at this point, the laser photon is over the limit. It's in a microwave field that should easily be ionizing any states anywhere in here, but yet when you look later, there are bound atoms. Okay. So here's actually a blow up of just the region of the limit. That microwave field will up to 70 volts per centimeter. And you can see this one. So you can see that this goes out about 350 gigahertz, about 10 photons over the limit. So our initial thoughts on this subject were that the simple man's model of ATI works fantastically well for microwave ATI. Okay, everything about it works fine. And so when you first look at these spectra, it looks just like an ATI spectrum. And so you try to use the simple man's model to explain this. Well, the microwave pulse is a long pulse, and so the maximum energy that you expect from the simple man's model is 3 times the quantum motive energy. This is the quantum motive energy here with the dotted line. So you can see that this clearly has nothing to do with the simple man's model. And why that is actually quite simple. The problem is that unlike the assumptions of the simple man's model, this electron is created in a Coulomb potential, and I can calculate the energy transfer from the microwave field as the force times the distance integrated, or the field times the velocity times the time. So if you are in fact created, the electron is created near the nucleus by the laser, which it certainly is, the velocity is almost entirely from the Coulomb potential. Okay. This is supposed to be V of R is approximately 2 over the square root of R. So the point is that the velocity here doesn't come from the microwave field, it's coming from the Coulomb potential. It's the square root of this kinetic energy. So most of the energy transfer is dominated by the first half cycle when the electron is in here. And then, since this all comes from the Coulomb potential, the energy transfer is linear in the electric field, not quadratic, like the simple model. And so actually, this is a graph of a simple model that this is the prediction of a simple model and as to the extent of the energy transfer. So, of course, this picture essentially assumes that there is a phase dependence, because I'm basically claiming that the electron, depending upon when I create the electron in this microwave field, it in fact will in fact wind up with a different energy. That's the same as the simple gas picture. And so we've in fact excited atoms in the presence of in the presence of a microwave field with a 2 picosecond laser pulse. So the microwave period is 56 picoseconds, so the 2 picoseconds is still short by comparison. So let's imagine that we excite the atoms to an energy here slightly over the limit. So the picosecond laser produces electrons that are going both to the left and the right. It has many cycles in this 2 picoseconds, so the electrons are going both ways. But if the field is pointing to the right, the acceleration is to the left, right, on all these electrons. So if the electrons are ejected moving to the right, they're slowed down. If they're ejected moving to the left, they gain energy and in fact become more energy. And a half cycle later, the roles are just reversed. But the point is that every half cycle, you will in fact be taking energy out of some of these electrons, and so they can in fact go from this energy down to lower energy. And so experimentally, does this by exciting with 2 nanosecond lasers of lithium. The picosecond laser goes about 250 gigahertz over the limit, And then we in fact move phase-locked a picosecond laser to the microwave field and move it around in time, and then look for the bound atoms later. So if this picture that I've just given you is right, there ought to be a phase dependence. So actually you can see the phase dependence. In fact, there's a clear oscillatory signal. These are the bound atoms detected subsequent to picosecond excitation in the microwave field. And basically it shows the 28 picosecond oscillation, which is twice the microwave frequency. Which I will point out is essentially the physics of this is exactly the same as the physics observed in experiments at Lund and also here, in which high harmonics of an attosecond pulse train that came from an intense infrared field, the combination of the two provided ions. The high harmonic produced is enough to get you near the limit within 1 IR photon. And in fact, if you change the phase of the IR field at which the attosecond pulse train comes, you see the same oscillation at half the IR period. So in this case, the phase at which you see more helium signal is when you're actually kicking the electrons over the limit, whereas we were doing it the other way around. We were starting up above the limit and coming down. So finally, I guess I would like to come to just one last point, which is these signals appear to be connected to the ionization limit. So to check that, we're going to do another experiment. But first I would like to point out that these signals actually go from 300 gigahertz over the limit. And you can see this structure is all spaced by the microwave frequency. Each of these peaks is 38 gigahertz apart. So, and in fact, this is all connected to the ionization limit. And the way that you can tell that is that if you apply a small static field, okay, what you do is push the limit down. And so these are in fact sections of that previous spectrum. This is with just our sort of the minimum stray field we can have. So we have this 38 gigahertz modulation. So these are the laser tuning energies. So this is the limit here. And this is now at these binding energies. Lots of photons, this many photons away. So when I apply an electric field, I push the limit down, okay, and you can see when I go up to 17 millivolts, this moves over. But it moves over exactly the same way if you look down at this depth of binding. If you keep raising the field, everything just moves. Now, of course, as you raise the field too much, it ionizes, and you just don't see anything left anymore. Okay, so it's clear that what we're observing are some kind of Floquet states that are based on high-lying states just below the limit, less than 2 microwave photons, and probably 1 below the limit. So in these states, the outer electron only comes back to the core rather infrequently. But just to put this in perspective, if you are in fact bound by 38 gigahertz, the Kepler frequency is 250 megahertz, or it comes back to the core every 4 nanoseconds. But if you actually measure the lifetime of those states, so if you tune the laser 2 microwave photons over the limit, the decay time is about 70 nanoseconds. Here is 60 photons below the limit. It's 150 nanoseconds. But even this time is, of course, much longer than 4 nanoseconds. So these electrons are clearly coming back to the core multiple times. I mean, it's not that we've just parked the electron out there in left field and it's never coming to the core. It's coming back, but it's not necessarily ionized. And the same is true of the Max-Born helium experiments. This is what they calculate to be their final state distribution. This isn't measured, these are calculated, but in any case, most of the population that they claim to be in states which have Kepler periods Kepler periods shorter than the laser pulse. So all of these states are states in which the electron revisits the core during the laser pulse. And finally, I would just like to point out that both of these experiments you can find suggested in a paper by Harvard-Muller about 14 years ago. So, in which he did calculations of how do you get superponder motive electrons in ATI. And his calculations showed that you get these superponder motive electrons when the intensity is such that states just below the resonance are brought into multiphoton resonance with the ground state and therefore populated. And he observed the same thing. I mean, that basically the electron will cruise around in one of these states. And when it comes to the core, okay, 4 things can happen. You can have ATI, making superponder motive electrons. You can have high harmonics generated. You could have non-sequential double ionization. Or nothing could happen. But eventually, these 3 will kill it. And so what happens is you slowly just lose the population. And I believe this is, in fact, what we are presently seeing. Okay, so finally, I think most, if not all of the one-electron phenomena that you can see with a bone-crushing laser, you can also see with Rydberg atoms and microwaves. Okay, with that, thanks for listening.
Questions or responses to this last one?
Would this also happen in pure hydrogen, atomic hydrogen?
Would what also happen?
The last phenomenon with the trapping and bouncing around.
I believe so.
Yes, we've done the calculation.
Oh, so you believe for sure then?
And I believe it. No.
Okay, here first.
I just wanted to ask you, at the very end you talked about high harmonic generation.
Yes.
But it wasn't clear to me if you would actually observe that.
Oh, no, we haven't observed. I was just pointing out that in the laser case, we have not observed high harmonic generation. In the laser case, if you have helium, you could imagine, well, maybe I missed something, but those are the 4 things I'm pretty sure will happen.
But you should be able to observe it then, because you have the analogous phenomenon.
Well, okay, one of the problems is that if they're harmonics of 10 gigahertz, this is really hard to see. I mean, you can't separate anything. We've never seen that.
I think also probably the target thickness would not be high. The target thickness would probably also be a little bit smaller for this kind of study. So I wanted to ask about, provoked by this, so one thing that has been studied a lot in strong field physics is molecules, and in particular the dependence on ionization dynamics on the relative orientation between the external field and, say, the molecular axis in the case of a diatomic. Would the similar thing exist in the case of a Rydberg molecule? Could such studies be done that? I mean, I've not thought much about it. I thought just now that it would be very interesting because of several reasons. Also, we know that the Born-Oppenheimer breaks down if we have a Rydberg molecule. But the question is if it's stable enough for a long enough time to see these things.
I'm sure it. Well, actually, you're as much of an expert on this than I am. Well, a problem in the molecules is often that they pre-dissociate before anything else happens.
Yeah.
However, if you make states of high angular momentum, they will sit there. But I think they basically behave more or less the same. If it's a Rydberg anything, and you put it in a microwave field, it usually doesn't care very much about what the core is. And actually,
Yeah, but of course, if it's high L, it goes like this, and then it's hydrogenic-like or atomic-like. But
well,
if it's not high L, it will be this.
okay, but if you're driving with a field, L doesn't mean anything. Okay, my feeling is it wouldn't.
No, it's a preparation. I mean, in the preparation step, of course, you also have these coherent.
But once you put the field on, L isn't any good as a quantum number. Bob and I argue about this sometimes, but I often think it's easier to think of them as star states. He disagrees, but anyway. But the other thing, one of my reasons for thinking it won't make any difference was back to Jan Mikkel's question, which is, I showed you pictures of ionization of sodium in which you could see a clear difference between m equals 0 and m equals 2. That's the difference between hydrogen that has no level crossings and something which does. But when you go up to high n states, the level crossings become so small and the frequencies become closer or bigger than the spacing between the levels, and you can't tell the difference. And so I have a feeling that a molecule will be exactly the same. Okay, this is the basis of 1 minute's thought.
Yeah, I think I would agree to the last argument you made, but on a more general grounds, I guess your equivalence works because everything is scaling in Coulomb problem. You don't have anything in your way, you can scale out quantities, so you have one scale free, and this is what you exploit, I think, by making the comparison of microwave to strong laser fields. But now, once you introduce the molecule, you have an additional time scale, and that's the vibrational or nuclear time scale. And I'm wondering if this would not limit, in the end, this complete equivalence.
Okay, the reason I think it probably doesn't kill it is the fact that when people do the Ziki experiments, they see things that live basically forever. Right? They're not supposed to be there. And I think that what happens when you wind up getting mixed states that are not pure low angular momentum states, you decouple from that slightly. Okay, that's an interesting question. But
My guess would be you could probably do the experiment, but I think the kind of orientational dependencies that you're used to seeing for ground state molecules, that's all going to be gone.
Yeah,
So
therefore
the molecule doesn't scale along.
And therefore, of course, there are things which cannot be captured by microwaves and Rydbergs. That's the point.
now that you make that point, I will also point out something else. So although I didn't really discuss this very much here, one of the reasons we started to do these experiments was I thought you could connect photoionization to field ionization. And in fact, you can easily tune the laser within 1 microwave photon of the limit. And I always thought, wow,